Hi, this is Paul from All About Digital. This is Chapter 3, Part 2 of a three-part series on Karnaugh Maps. In this video, we're going to learn the structure of Karnaugh Maps and how they're used to reduce Boolean expressions. So please like the video, subscribe, and list your comments below. Enjoy the video. Thank you. This is Chapter 3, Part 2, Karnaugh Maps. In this video, we're going to learn the structure of Karnaugh Maps and how to reduce and optimize Boolean expressions using these Karnaugh Maps. Okay, so now that we've created a truth table, how do we minimize these functions from the truth table? We could use Boolean algebra, which we did in Chapter 2, and we can use all the laws and rules, but it gets fairly complex. And sometimes you make mistakes. Well, you make mistakes whatever you do, but it's easier, I think, to make a mistake in Boolean algebra when you're using the laws and rules, because it gets so complex when you have multiple variables, and it does with this new technique that we're going to define right now, and it's called the Karnaugh map. And the Karnaugh map is just a pictorial form of a truth table. Now let's talk about a couple of truth tables for the AND function and the OR function. These two truth tables below here represent the AND function and the OR function. The AND function is the Boolean multiply. And as you can see, the only time the Boolean multiply is equal to a 1 is when both A and B are 1 in this point right here. So we know that 0 times 0 equals 0, and 0 times 1 equals 0, and 1 times 0 equals 0, and of course 1 times 1 equals 1. All right, let's look at the OR function. The OR function says that anytime A or B is a 1, the output is a 1. Okay, let's look at the Boolean expression for that. 0 plus 0 is equal to 0. 0 plus 1 is equal to 1. 1 plus 0 is equal to 0. Equal to 1. And 1 plus 1 is equal to 1. Again, that's not the modulo 2 sum, that's the Boolean sum. Okay, let's look at the Karnaugh maps, or K-maps, associated with the AND gate here and with the OR gate. You can see that the truth table again shows that when A times B is equal to a 0, 0, 0, 1 or 1, 0, the output is equal to a 0. The only time the output is a 1 is when both A and B are a 1, as shown. The Karnaugh map lists the inputs on the outside, A and B, and the outputs are inside the cubes. These are called cubes inside the Karnaugh map. So the intersection of A and B, 0 and 0, occurs right here, and that is associated with this row in the truth table. The intersection of A is a 0 and B is a 1, A is a 0 and B is a 1 right here, occurs right here. This is where A is a 0 and B is a 1. Where A is a 1 and B is a 0, that occurs right here. That's the intersection of B and A for a 1, 0 right here. And when both are 1, that occurs right here, 1, 1. Okay, so again, the Karnaugh map is just another pictorial representation of the truth table with the inputs around the outside and the outputs inside the cubes inside the Karnaugh map. Let's do the OR gate. The OR gate shows that for the Karnaugh map, or the truth table actually, the only time that the output is a 0 is when both A and B are a 0, and that occurs right here, and that is at the intersection of A and B as a 0. This one right here. When either A or B is a 1 or both, the output's a 1, and so that's these other three locations in the map. Okay, again, this is the Karnaugh map for an AND function. This is the Karnaugh map for an OR function. So, as far as the Karnaugh maps are concerned, we don't need to use Boolean algebra to reduce the sum of products form as written from the K-map. That's because the layout of the K-map places cubes adjacent to each other, which makes it easy to minimize by grouping ones into subcubes and limiting the variable that changes. And we'll show that when we start doing some reductions using Karnaugh maps. So the point here is that you don't need to use Boolean algebra. The adjacencies are set with the Karnaugh map the way it's laid out. All right, here is a couple of representations of two different Karnaugh maps, one for the min-term functions and one for the max-term functions. And what we're going to look at is the way you lay out the Karnaugh map. Over on the left here is the function. It's got 16 possibilities, binary 0 through binary 1, 1, 1, 1, 0 through 15. And that translates directly to the Karnaugh map. And the Karnaugh map has 4 rows, 1, 2, 3, 4 rows, and 4 columns, 1, 2, 3, 4. And you split the variable up so that on the top we have AB. So all the combinations of AB, which are 0, 0, 0, 1, 1, 1, and 1, 0, 0, 1, 3, 2, or 0, 1, 2, 3. And then on the column side, we list all the combinations for the two variables CD. CD can be 0, 0, 0, 1, 1, 1, 1, 0. Notice that we count, we'll go up to the AB section here. We go 0, 1, and then we go 3, 2. Okay, why do we do that? Well, the map is laid out so that this cube right here, for instance, is adjacent to this cube. What do we mean by adjacent? We mean that when you travel from this cube to this cube, there's only going to be one variable change. Well, what variable changed? Well, C and D did not change. They stayed 0. B did not change. A changed from a 0 to a 1. So there's only one variable change when you transition between this cube and this cube. There's only one variable change. And in fact, you can look at any cube on this map and you look at the transition from here to here. There's only one variable that changed. CD didn't change. It's a 1 and a 0 for these two. And up here, A is a 0, changed from a 0 to a 1 from here to here. But B stayed at a 1. So the only variable that changed was A. It went from a 0 to a 1. So there's only one variable change, so we're adjacent. How about this cube right here and this cube right here? Let's look at variable changes, see if there's only one variable change between these two. If we look at this M8 right here, we see that C and D are a 0 right here, and down here, C and D are a 1, 0. So the variable that changed was C. So C went from a 0 to a 1. So there's one variable change right here, and that's a C. Let's look at from here to here, AB. Did AB change from here to here? No. AB stayed a 1 and a 0. So the only variable that changed was C, and it went from a 0 to a 1. So these two cubes are adjacent. That is, there's only one variable change between the two. Okay, and in fact, you can look at any two cubes here. This cube to this cube, 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 and any two cubes on here, they're all adjacent. Okay, what I did was I showed this Karnaugh map with respect to which standard sum of product forms or minterms are located within, are represented by this cube, this location in this cube. M0 is the first one here. That's 0, 0, 0, 0, 0, 0, 0, 0. M1 is 0, 0, 0, 1. So M1 is down here. Okay? As you go down, these are all mapped into an individual cube on the Karnaugh map. Now you notice this will go, it goes 0, 1, and then 3, 2. And the reason you count 3, 2 is to maintain the adjacency between these two right here. As we move from left to right in the Karnaugh map, this one goes 4, 5, 7, 6. Okay, and the reason we go from 5 to 7 and then 7 to 6 is to maintain the adjacencies between these two cubes. Now we go all the way to the end here, and we get 8, 9, 11, 10. Okay, and in the middle here we get 12, 13, 15, 14. That's because that when we look at the combinations across the top, we count 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, 3, 2. The same down here. We do 0, 1, 3, 2. And the reason we do that is to maintain the adjacencies between all these cubes. Okay, it's important. Adjacency is important, and we'll talk about that. Okay, these are all the min terms. These are the max terms. Big M0, it's the same locations. Again, this is the ones of the function like we learned, and this is the zeros of the function. Okay, all the zeros will map into this max term map, and all the ones will map into this ones map. Oh, you could have all the ones and zeros in the same map, actually. Okay? As we discussed, all cubes in the K-map are adjacent to each neighbor cube. That is, there's only one variable change between adjacent cubes. Okay. Let's look at a Karnaugh map with the function. So on the left here, we have a function. It's 8 combinations, 0 through 7. And this is our function right here. 0, 0, 0 is a 1 right here. 0, 0, 1. 0, 0, 1 is right here. 1, 0, 1. 1, 0, 1 is right here. And 1, 1, 1 is right here. Okay? So we've mapped all the ones, there's 4 of them, into this Karnaugh map right here. Okay? This is a 3-variable Karnaugh map. Okay, so you can write the function as the sum of 0, 1, 5, 7. And that's what we have here, 0, 1, 5, and 7. If you look at the max terms, it's the same thing. We're mapping the zeros of the function. There's 1, 2, 3, 4 zeros. And that's how they map into this Karnaugh map. Okay? All the zeros are mapped. There are, again, really, there's these zeros right here, but I separated just to make them more distinct. So here's the 4 zeros, and these are the max terms associated, or the standard sum terms associated with those zeros. And again, the max terms are the product of max term 2, 3, 4, 6. 2, 3, 4, 6. So what we're going to show is it's really not necessary now to use Boolean algebra to reduce the standard, to reduce the SOP form, sum of products form, as written from the K-map. This is because the layout of the K-map places cubes adjacent to each other. And adjacent means there's only one variable change between cubes, and we'll discuss why that's important. And we're going to kind of discuss what the adjacency means in this 3-variable map. There's 4 rows in this map. Row 1, row 2, row 3, and row 4. There's 2 columns. Column 1, this one here, and column 2 right here. It's column 2 and column 1. And then row 1, 2, 3, 4. Okay? Now, row 1, this is all of row 1, is adjacent to all of row 2. So this whole row is adjacent to this whole row. Okay? And row 2, this whole row 2 right here, is adjacent to row 1 and row 3 because it's right next to it. Okay? And row 3 is adjacent to row 2 and row 4, the one above and the one below. And column 1 is adjacent to column 2. Column 1 is adjacent to column 2. So row 1 is adjacent to row 2, this one here, and then also it loops around and it's adjacent to, it's like a toroid. Loops around and it's adjacent to row 4. So every row is adjacent to 2 other rows. Row 1 happens to be adjacent to the one right next to it, row 2, and the one at the bottom down here. Okay, row 2 is adjacent to row 1 and row 3. Row 3 is adjacent to row 2 and row 4. Row 4 is adjacent to row 3 and row 1. Okay, clear as mud, right? Okay, here's a 4-variable map. And in a 4-variable map, again, instead of having 2 columns, we have 4 columns. We have row 1, row 2, row 3, and row 4, but we have 4 columns. 1, 2, 3, 4. Okay? Now in this map, again, row 1, this whole row, is adjacent to this whole row 2, and then all loops around, and it's adjacent to this whole row down here. So the row 1 is adjacent to row 2, which is right below it, and this one down here. Okay? Now, row 2 is adjacent to row 1, which is right next to it, and row 3, which is right next to it. Okay? Row 3 is adjacent to row 2 and row 4. Okay? Every row is adjacent to 2 other rows. And the key word is adjacent. Okay? Now let's look at row 4. Okay? Now, the bottom row is adjacent to the top row. And vice versa. The top row is adjacent to the bottom row. Okay? So every row is adjacent to 2 rows. So row 4 is adjacent to the one that's next to right here. And also row 1. Okay, so it's adjacent to this one and adjacent to that one. Okay, and we're going to see why that's important when we start doing minimization. So you just kind of have to realize that that's the way it is. Okay, let's look at a 5-variable map. What's 5 variables mean? We have a function of 5 variables. In this case, we have A, B, C, D, and E. Okay. We have 2 4-variable maps. These 2 right here. This whole map on this side right here, the variable E is a 0. This whole map over here on this side, the variable E is a 1. Okay? And if you start looking at all the adjacencies, this whole map is adjacent to this whole map. This row is adjacent to this row. Oops. Let me take all this off again. On the right here, it describes all the adjacencies. Okay, so let's go back to this one over here. This row is adjacent to this row because it goes around, right? And also this row, but it's also adjacent to the row in the other map over here, to this one over here. Okay. So row 1 prime is adjacent to row 2 prime and 4 prime. And row 1 is adjacent to row 1 prime. So these are adjacent to each other across between these two variables right here. Okay, so we're going to talk about this a little bit more, but you can see that, again, this cube right here is adjacent to this cube. It's also adjacent to this cube and this cube. Okay? All right, we're going to do some minimizations and hopefully it'll get clear. So now, how do we use these? First of all, we plot the ones in the Karnaugh map and then form subcubes to cover the ones in the expression using 1, 2, 4, or 8 adjacent cell subcubes. We'll talk about what that is. And then write the expression for each cover. Okay, so let's do this one first. Okay, we have a function, ABC is equal to the sum of minterm standard product terms, 0, 2, and 6. Okay? That's this truth table right here. 0, 2, and 6. Okay? So let's minimize these. First of all, what we do is when we're going to do introduce something called a cover. And a cover, it means you're going to circle the ones in your Karnaugh map. Okay? The idea is you want to circle all the ones in your Karnaugh map, and once you've circled them, you can write the function from those circled functions. You can circle a function with either a single 0, that's called a cover. You can do a single, GLE. Okay, you can do a double. You can do a 2 variable map. You can do a 4 cover, 4-1 cover, 8 ... It's a power of 2, 2 to the n. The single is 2 to the 0. So you can cover. You can cover the ones with either single 1, 2 ones. You can cover 2 ones at once. You can cover 4 ones at once. You can cover 8 ones at once. And what we'll show is the more you cover, the more minimal the solution will be. Okay, so let's go ahead and run this example right here. So we know that all of row 1 right here is adjacent to row 2 and also adjacent to this row down here. Remember, this is adjacent to the bottom row. Okay, so what we're trying to do is we're trying to cover, in other words, draw a circle around as big a cover as we can. In other words, cover as many ones with one cover as we can to get a more minimal solution. So we see that we have a 1 here and we have a 1 here. So we can create a cover right here of these 2 ones. So these 2 ones are adjacent to each other because they're on the top and the bottom. And because they're adjacent to each other, we can cover them with a 2 function cover. So we're covering 2 ones, and the idea is to cover all the ones and then you're done. So we cover these 2 ones. Okay. So now we want to write what's the product term under this cover. Well, the way you do it is you look at the variables that change underneath this cover right here. So in this particular cover, we're covering this cube and this cube. So in this cube right here and this cube, if you look both of them, what variable doesn't change in this column right here? Well, the variable that doesn't change is the A. And the A happens to be a 0, so we write A bar. Okay, and then we have to look at the B and C. If we look at the B and C values, there's 4 values. And when we look at the cover of this one from here to here, what changes under this cover associated with this cover? Well, B and C is a 0, 0 here, and B and C is a 1, 0 here. And we can see that the B went from a 0 to a 1 under this cover, okay? So what that says is the b drops out of the product term. So what we're left with is whatever the value of c is, and the c is a 0, so that's a c bar. So for this 2 function subcube, okay, the value of this product term is a bar c bar because b dropped out because it changed from a 0 to a 1. There was a variable change that dropped out. So that's subcube number 1 right there, okay? And if we go over here, we see that subcube reduces to a bar c bar because a and c are 0 under the curve. A and c remain, they don't change. Under the cover, this one right here, okay? Now, we have another one right here. We have to cover all the ones, that's the idea. We have to cover all the ones on the K-map. Okay, we've already generated our first term right here. So now let's look at how do we cover this one? Well, we could just do a single circle around it, okay? And then you just write down what the value is. The value would be whatever the value of A is a 1. So we get A, and then B is a 1 and C is a 0. So we get A, B, C, 0. C bar, A, B, C bar. But we don't have to cover just one. We can cover 1, 2, 4. And in this case, we can cover 2 because we can cover a 1 that's already been covered. And that's okay. We can do that. So we cover these 2 ones right here because they're adjacent to each other. So for this subcube, we notice that B and C, B is a 1 and B is a 0 right here. So we know that we have B, C bar, B, C bar under this cover right here. And we see that A went from a 0 to a 1. A went from a 0 to a 1 from here to here. So A drops out because it changed. So what we're left with is subcube 2 is equal to B, C bar. Okay? Again, B is a 1 and C is a 0. Okay? So we've reduced, we could have 3 standard product terms, 0, 2, 6, okay, and then reduce all those using Boolean algebra. Or we can use a Karnaugh map and cover them with 2 cube covers like this, and we can eliminate, go from 3 to 2 product terms, and we can eliminate variables out of each of these product terms. So the final answer is the function is equal to subcube 1, which is AC bar, plus subcube 2, which is BC bar, so it's equal to BC bar plus A bar C bar. Okay, in summary here, if a variable changes underneath the cover, it drops out of the expression. So A changed from a 0 to a 1 in this expression. Under the cover, you look under the cover, from here to here, A went from 0 to 1. It drops out then. It's gone. And we look down here, what didn't change? Well, B and C did not change. The first cover, this cover right here, this one. Okay. Let's make that a little easier to see here. The first cover, we had these 2 right here. Again, A didn't change. A from here, from this cover to this cover, only on the cover, stayed as an A. It was an A bar, actually, as I say. A didn't change. But we look as we go from this point right here down to this point, we see that B changed from a 0 to a 1. So B just drops out. And what we're left is what the value of C is. C is a 0. So we have C bar. So this becomes A bar, C bar. And that's what that is right there. Okay, so we just need practice, and you work on these, and pretty soon it becomes fairly simple because you can identify which way to cover things. Okay, so let's do another function. Let's do another simplification. And in this simplification, we're going to try to cover these particular ones, first of all, looking to cover it with the maximum cover, which in this case would be a 4 cover. You can either do a 1 cover, which would be just one of them. You can do a 2 cover, because anything is next to each other is adjacent. You can do a 2 cover, or you can do a 4 cover. Okay? So it's in powers of 2. 1, 2, 4, 8. 16. Well, you normally don't get that large. So let's see what we can do here. Okay, so again, let's define this function. We want to find the minimal expression for this function right here, defined as the sum of product terms in the min-term representation. We have 0, 1, 2, 3, 4, 5, 8, 9, 10, 15, which is the ones of the function. Here's the ones of the function. Okay, and here's the ones of the function. And here's a 1. Now that translates, we re-put to a 4-variable map, because we've got 4 variables, w, x, y, z. This is the Karnaugh map. And again, you number them 0, 1, 3, 2, 0, 1, 3, 2. And all these ones map into the Karnaugh map as such. Okay? So for this particular example, we're going to split up. We're going to split up into, because I know there's going to be like 5 different covers. We're going to do 3 covers first. We're going to split the map up because it gets kind of messy. And then we'll do the final 2 covers. So let me explain a little bit more about what we're doing. So I took this same map right here, the same Karnaugh map, and I redrew it 3 times. There's 1 time, 2 time, 3 time. So we're going to do an individual cover on each of these maps to define the product term for that particular cover. And this is what it comes out to. Okay, so for the first cover, I could use a 4, I can cover 4 with this particular covering right here, because there's 4 adjacent ones. So there's 4 adjacent ones, I can cover 4. Now, let's write the product term for this 4 right here. And again, what do? We look at underneath the covering, what variables changed. Well, we know that underneath this covering, as we go down, y and z all change. They all change, so y and z drops out. What doesn't change? W and x stay the same, and they happen to be w bar, x bar. So for this particular cover, we've covered these 4 ones. This is the product term that the reduced product term that we get, okay? Now, let's go to the same Karnaugh map, and we're going to get some more ones. The idea is to cover all the ones on the map. So we're going to go to blue here. And as we know that these 2 right here are adjacent to these 2 right here. So we can cover these 2 with these 2. Okay, we've already covered these 2 over here. Do we have to cover them again? Yeah, well, you don't have to, but if you do, you can. If it's already covered, you can reuse them again to help you get a larger covering to get a more minimal solution. So we reuse these 2 ones over here to help us cover these 2 ones right here, and we get a 4 covering. So we've covered now these 2. We've picked up these 2. And so we'll call that S2, subcube 2. And let's calculate what this product term is going to be. Let's look at first what changed from here to here. Well, the x went from a 0, the w went from a 0 to a 1, so it falls out. The x stayed at a 0, so that's x bar. So we have x bar right here. Let's look at the column, yz. Yz, was as we go from here to here, we see that y stays at a 0 and z changes from 0 to 1, so z drops out, so we're left with y bar. So subcube 2, or product term 2, reduced, is x bar, y bar. Okay? So now we've covered these 2, these two, and these two. So what we have left is this one, and this one. Okay? So let me take away some of my mess here. All right, let's go down to this same map, and we're trying to cover this one. We're gonna go for this bottom one right here, okay? And we could just circle this bottom one and write out the product term, but because it's adjacent, the four corners on this four variable map are adjacent. So if you have four ones in the four variable map, they're all adjacent, you can cover those all as such. Okay, so for this 1, 1 down here, we use a for cover, and we're reusing ones that we've already used, but those are helping us reduce this product term that we're going to get for this one right here. So our choice would be just do it a one cover, and the product term would be, if we had a one cover, it would be WX bar YZ bar. Okay, so it'd either be that, or if we reuse these ones here that we've already used before, which is perfectly okay, we can reduce it down to X bar Z bar. So that's why we reuse them. We drop two terms out of this function right here, out of this product term. Okay? So now we still have two ones left that we haven't gotten. We have this one right here. Oop. We have this one right here, and we have this one right here. Okay, let's go to the next map. Okay, for this one, we have this. We're trying to get this one right here, that one, and everything else is covered except that one. So we're going to reuse this one over here that we used in subcube 1 to help us define a minimal term for this one right here. Okay, so we have a two covering, so we know one variable is going to drop out, and which variable is that? Well, the one that changed from here to here is x. So x dropped out, and so we have w bar, because it's a 0, and y bar z bar. So S4 is equal to w bar, y bar, z bar. Okay? Now, let's do the final one here. This is 0 right here. Now, everything else is covered on this map. We've got all covered. We have all our product terms. This one here doesn't combine with anything because this one is not adjacent to anything. There's not a one here. There's not one there. There's not one above. And there's not one below. So there's no adjacent ones to this one right here. So you just have to use it by itself because you have to cover all the ones. So subcube 5 is just going to be equal to Wx, because it's a 1, 1, yz. Wx, yz. Okay, so kind of reviewing this, this is the coverings that we made. And we made 5 different coverings to help minimize this particular function. The first one that we did was we covered 4. Okay, and that 4 translated to W bar, X bar. Okay, and the next one we did was the blue. We did these two. We did these two in the corner over here, and then these two over here. And that translated to, because we have a covering of 4, 2 variables drop out, and it translated to the product term X bar, Y bar. For the third one, we did the 4 corners. The 4 corners on a map are always adjacent. So you can cover all 4 corners. And remember, we picked up this one right here. We picked up that one right there, okay? And so that came out to be X bar, Z bar, okay? Now the fourth one we did, we had this one right here, a one right there, and we used the one adjacent to it to help eliminate one of the variables. Again, if you cover with 2, you drop out one variable. If you cover with two, if you cover with two, you drop one variable. If you cover with four, you drop two variables. If you cover with one, you don't drop any variables. Okay, so we covered with two, we drop one variable, and so S4 is missing one of the variables, which is X, and it comes out to be W bar, Y bar, Z bar. S5, we only have a one cover, so nothing drops out, no variables drop out. We just have to write the standard product term, which is they're all ones, Wx and Yz. So S5 is equal to Wx, Yz. Okay, then the reduced function is equal to subcube 1, which is this one up here, plus subcube 2, plus subcube 3, plus subcube 4, plus subcube 5. And that's equal to these product terms. W bar X bar plus X bar Z bar, Y bar plus X bar Z bar plus W bar Y bar Z bar plus WX YZ. Okay? So you can do them, you can make multiple copies of the same four variable map, and you can do like we did on this example, and you can just do them individually. But it's to your advantage to use ones that are already covered to give you a larger covering of either a 2 or a 4. Okay, and so this is the minimal expression for that original function. Okay, we didn't use any Boolean algebra at all. All we did was Karnaugh maps and coverings. In this video, we discussed the methodology for taking a Boolean expression and reducing it using the Karnaugh mapping techniques. The mapping techniques made the reduction process much simpler than using only the laws and rules of Boolean algebra. In the real world, mapping techniques are used almost exclusively because of the ease of minimization of the Boolean expression and the ability to generate minimal expressions in either the SOP or POS forms. Well, that's the end of part 2. Please like, subscribe, and leave comments. I hope you enjoyed the video, and make sure and watch part 3. Thanks for watching.